Good morning, all of you. In the last class, we studied what is autocorrelation of a random process. How to find out autocorrelation RxX. Today, we'll be defining what is power spectral density and we'll be seeing some solved problems to understand how to find out the power spectral density of a random process. For any random process x of t, the power spectral density PSD is defined as limit t naught tends to infinity e x t naught of f the whole square by 2 t naught. Or in simplest of all the terms, power spectral density is the Fourier transform of the autocorrelation function of a random process. This means that in a stochastic process, we do all the analysis in time domain. If we want to understand the frequency perspective or in frequency domain, what we do is that we convert this autocorrelation function by using its Fourier transform, and this form is known as power spectral density of a random process. So I'll repeat this very important definition once again. Power spectral density is the Fourier transform of autocorrelation function. We are analyzing autocorrelation in terms of its frequency. Okay, so what we do whenever we convert anything from time domain to frequency domain, we find out its Fourier transform, right? So here the Fourier transform of autocorrelation function is defined as its power spectral density. Okay, and this is known as Wiener-Khinchin theorem. Wiener-Khinchin theorem. Sx of f is equal to Fourier transform of the autocorrelation function. Autocorrelation function is denoted by Rx of tau. A recap of what is meant by autocorrelation function. Autocorrelation function is the relationship of the same function at a different point of time. We have two types of stationary process, wide sense stationary and strict sense stationary. In wide sense stationary, that is WSS, we have two conditions. First condition is that the mean should be a constant and the autocorrelation function should be time invariant. Now we'll see some properties of power spectral density. Power spectral density Sx of f is always a real function. We'll never have negative functions. The least value it can take is 0. Is an even function. That means Sx of f is equal to Sx of minus f. The average power in a random process is given by Px is equal to minus infinity to infinity Sx of f df. So if you are asked to compute, if you are asked to calculate the average power of a random process given your power spectral density, Px of x will be equal to minus infinity to infinity Sx of f df. The autocorrelation function of an aperiodic power signal is given by Rxx of t is equal to e raised to minus tau square by 2 sigma square. You are asked to find the power spectral density and the normalized average power content of the signal. The autocorrelation function is given to you. You are asked to find out the power spectral density. So how will you find out? Sx of f is equal to integral minus infinity to infinity Rxx to e raised to minus j omega t or 2 pi f, whatever it is, dt. Power spectral density is given by Sx of f is equal to integral minus infinity to infinity Rxx of t, that is autocorrelation function, into e raised to minus j omega t dt. So please solve it out. On solving the integral, you will get the power spectral density to be equal to root of 2 pi sigma square e raised to minus j omega sigma square by 2. In the next part of the question, you are asked to solve for the normalized average power. And normalized average power is nothing but the autocorrelation function Rx of 0, right? Rx of 0 is equal to 1. Rx x of 0, when you equate to 1, you get the normalized average power. The normalized average power is given by Rxx is equal to, Rxx of 0 is equal to 1. Next question, the autocorrelation function of a random telegraph signal x of t is given by Rx of t is equal to e raised to minus 2v absolute of tau, where v is a constant. You are asked to find its power spectral density. You are given the autocorrelation function Rx of tau and you are asked to find out the power spectral density. What is power spectral density? The Fourier transform of the autocorrelation function, right? Let us look for the solution of this problem. As discussed above, power spectral density is a Fourier transform of the autocorrelation function. Rx of tau into integral into e raised to j omega t dt. Omega t is in other terms 2 pi f. On solving the integral, you will get that answer to be v by v square plus pi square t square. Shall we do the next problem? The output of the previous problem is applied to a low-pass filter as shown below. Determine the power spectral density and the autocorrelation function of the random process at the filter output. So how will you do this? The output of the previous problem is applied to a low-pass filter. You are asked to find its power spectral density and the autocorrelation function. So let us see how to solve this problem. Now the transfer function of this filter is given by, we know that it is a low pass filter, so the transfer function will be h of f is equal to 1 by 1 plus j2 pi f r c, where r is the resistance given there and c is the capacitance. Therefore the power spectral density will be equal to the output, no, previous output Sx of f into h of f the whole square modulus. So Sy of f is given by Sy of f, the output at the low pass filter, is given by the square of the transfer function Sx into the input power spectral density from the previous one. So now let us expand this. And solve for Ry of t. Another problem. A zero mean stationary process x of t is applied to a linear filter whose impulse response is defined by a truncated exponential. H of t is equal to a e raised to at when t is between 0 to t or 0 otherwise. Now you are asked to prove that the power spectral density of the filter output y of t is given by Sy of f is equal to a square by a square plus 4 pi square f square 1 minus e raised to at cos 2 pi ft plus e raised to minus 2 at Sx of f, where Sx of f is the power spectral density of the filter output. This problem is similar to the previous one. So like what we have done now, previous problem, we are given the transfer function here, minus infinity to infinity h of t e raised to minus j 2 pi ft dt, 0 to t, because for the rest it is 0, as given a e raised to at e raised to, and solve this integral. On solving this integral, what you will get? H of f will be equal to a by a plus j 2 pi f 1 minus e raised to minus at cos 2 pi f t minus j sine 2 pi ft. So we'll be finding out the hf square and sy of f, like what we have done for the previous problem. Like what we have done for the last problem, we'll be doing the same here too. If you have any doubts or any clarification regarding the explanation, you can ask me anytime. I hope all these things are very clearly explained and understood to you automatically. Consider a random process x of t defined by x of t is equal to sine 2 pi fct. Fc is the frequency, random variable uniformly distributed over 0 to w. Show that x of t is non-stationary. And I have given you a hint also. Examine specific sample functions of the random process x of t for the frequency f is equal to w by 4, w by 2 and w. So let us look into the features of the random process. Now in the illustration now what I have given you below, I have drawn the function sine 2 pi ft at different points, okay, with different range of frequencies. One for t is equal to w by 4, w by 2 and for w, okay. So when the frequency is w, we draw the function sine 2 pi w t. For w by 2 sine 2 pi w by 2 t. For w by 4 sine 2 pi w by 4 t. To show that x of t is non-stationary, we need to only observe that the waveforms illustrated at 0, positive for 0, in between t to 2w, and negative for 1 by 2w, minus 1 by 2w, I'm sorry, between 0 and the first half of the wave and the second half of the wave. So now let us observe the probability density function of the random variable x of t1 obtained by sampling x of t at t is equal to 1 by 4w is identical to the negative argument. Whereas the probability density of function of the random variable t2 obtained at the sampling time x of t at t is equal to minus 1 by 4 w is non-zero only for negative arguments. So in order to prove that any random variable is a non-stationary process, what we are supposed to do is that we have to prove that fx of, so if you are supposed to prove that a random process is non-stationary, you have to prove that fx of fx of t at one point of time is not equal to fx of another t2, right? Any other point. Here both these values are not equal, therefore it is non-stationary. Similar one, like what we have done previously. Now we are considering another one, sinusoidal process, where we define the random variable x of t to be a cos 2 pi fct. Frequency is a constant here, and the amplitude a is uniformly distributed according to the function given below. The amplitude is equal to 1 for a value between a between 0 and 1 and 0 otherwise. Whether this process is strictly stationary or not. You are asked to find out whether this process is strictly stationary or not. So let us draw the distribution function fx of x1. Okay. Since the amplitude is uniformly distributed as given, fx of 1 of x1 will be 1 by cos 2 pi fct1. This is the distribution for a uniformly distributed function. Okay. So we'll be plotting the distribution function here. Now you will get it like this. A square function. So this is how we determine that this process is non-stationary. We'll give x of I plus tau, and then we'll see that f of x of I and x2, that is the second one, are not equal, and in that case, so it is non-stationary. When the probability distributions at two different points of time are equal, it is called as stationary. If they are not equal, it is non-stationary. So thank you all. Thank you very much for listening to me.